it provides information about the shape, turning points, local min-max, and I think the camera's on. Just a second. Complete the following table using the equation and graphs given. Oh, let me hide that actually. So let's see. What is the degree for this example here? Let's fill this out. So here the equation is x squared. So we know the degree of this polynomial is 2. Is it an even degree or is it an odd degree? Well, clearly it's even because 2 is an even number. Leading coefficient. In this case, our leading coefficient is 1. End behaviors. So as x goes to positive infinity, what's happening to y? Y in this case is also going to positive infinity. As x goes to negative infinity, y is also going to positive infinity because it's just going up and up. Number of turning points. So this has 1 turning point, and number of x-intercepts, it has 2 x-intercepts. So that's, basic stuff. Nothing too difficult. Let's continue. In this example here, what is the degree of the polynomial? Remember, the degree is just the highest exponent value. So that's 4. And is that number even or odd? Well, that's clearly even. The leading coefficient is 3 in this case. And the end behavior is as x goes to positive infinity, y goes to, as x goes to negative infinity, y goes to positive infinity, and x goes to positive infinity, y also goes to positive infinity. Number of turning points. So here, how many turning points do we have? Well, let's count how many local max and mins there are. So there's 3 in total, so 3 turning points. And number of x-intercepts, in this example, there are 0 x-intercepts because the graph doesn't intersect the x-axis. So yeah, that's, and we can check our answer to see if I'm doing it right. Oh, I forgot to label from which quadrant it's starting and ending. So I apologize for that. That is something that I should have done. So it's starting from quadrant 2 and it's ending in quadrant 1. So remember, we always read from left to right. That's this kind of thing. So, and this also just happens to be from 2 to 1. All right. Oh, let's hide that. Question number. Let's do the next one. Oh, okay. Here we go. All right. In this example, once again, what is the degree? Well, it's 3. Is that odd or even? Well, that's clearly an odd number. Shoot, what were they? Should have copied the headlines. Leading coefficient. Leading coefficient. Oh, it's 1 because it's there. End behavior. So end behaviors, as x goes to negative infinity, y is going to. So when x is, if you start from the origin and going to the left, x is getting smaller and smaller. What's happening to the graph? It's going down. So y is also going to negative infinity. When x is going to positive infinity, meaning when x is getting bigger and bigger, what's happening with y? Well, y is also getting bigger. It's going up. So y is going to positive infinity. And quadrants, this is quadrant 3, so quadrant 3 to quadrant 1. Number of turning points, that was this one. So clearly there's 2 turning points, 1, 2. 2 turning points, and a number of x-intercepts, 1, 2, 3. 3 x-intercepts. Here we have a degree of 4. We know that's an even number, and we know that the leading coefficient is -1. So in this case, it's quadrant 3 to quadrant 4. And as x goes to negative infinity, y is going to negative infinity, y is going down, and as x goes to positive infinity, y is also going to negative infinity because is going down both times, right? Number of turning points. So here we have a maximum, here we have a minimum, here we have another maximum. So these are all local. Those are 3 turning points. And as for x-intercepts, we have 1, 2, 3, 4. 4 x-intercepts. And we can take a look at the answers, and I should, yeah, I should be right. I'm not going to go over this. This is basically very simple now. Just look at the exponent, and it's an even number, and then leading coefficient, and then and behaviors and whatnot, and number of turning points. Okay. Oh, and there's more examples of that. So yeah, I don't think there's anything tricky happening here. They're all basically straightforward, just looking at the graph, determining the number of turning points and x-intercepts. All right, this is the important stuff. Summary of findings. So a little bit of review of what's going on. Welcome. So a polynomial function of degree n has at most n-1 local max / min points or turning points. What that means is if I have a polynomial function, let's say degree of 5, that means at most the maximum amount of turning points I can have are 4, n-1, so 5 minus 1 is 4. It doesn't mean that it has to have 4 turning points, but that's just the maximum amount possible. So this is important because you're going to use this knowledge to discover unknown graphs or unknown functions given some limited information. So you need to know, use these, this knowledge. So that's number of turning points. Now, a polynomial function of degree n may have up to n distinct zeros. What that means is, if I have a polynomial function with, let's say, y equals x to the power 4, so n is 4 because that's the highest value. It can have 4 possible x-intercepts. Remember, may have up to, meaning it doesn't have to have 4 x-intercepts. But we have 2 more points of information that are very important, crucial pieces of information. So if your polynomial function is odd degree, it must have at least 1 x-intercept and an even number of turning points. So now using this knowledge, you can actually figure out what the degree is if it's unknown to you, because we know that odd numbers have to have at least 1 x-intercept. So automatically, if the graph doesn't have any x-intercepts, we know that it's an even degree. And if it has at least 1 x-intercept, that doesn't necessarily mean that it's odd, but it just means it's possible. Because remember, even degree functions can have a single x-intercept. For example, y equals x squared is an example of having 1 x-intercept, but x squared being an even degree. So just don't think that, oh, it has 1 x-intercept, it has to be an odd degree. No, just be careful with that, okay? But the even number of turning points, that's very important, because an odd degree can only have an even number of turning points. So if it has a single turning point and a single x-intercept, then by definition it has to be even because of the even number of turning points. And we're going to get into examples like that, so I'm kind of getting ahead of myself. But yeah, and then next piece of information is a polynomial function that has an even degree. It may have no x-intercept. Remember, may have no x-intercepts, but has to have an odd number of turning points. That's always true, so that's important. And then an odd degree polynomial function extends from the 3rd quadrant to the 1st. If it has a positive leading coefficient, or from the 2nd to the 4th if it has a negative leading coefficient. And examples are drawn here. And they have opposite end behaviors, which is something I've been saying throughout this whole lesson. And then an even degree either goes from the 2nd to the 1st if it has a positive leading coefficient, or from the 3rd quadrant to the 4th quadrant if it has a negative leading coefficient. And even degree polynomials have the same end behavior, meaning y is always both times going to the positive infinity or both times going towards negative infinity. Example 1. Oh, okay, let's see if we can do example 1. All right. Describe the end behaviors of each function, the possible number of turning points, and the possible number of zeros. Use characteristics to sketch possible graphs of the functions. So here we have example 1a. We know that this is an odd degree polynomial because the highest exponent is 5. So it has an odd degree. That means the maximum possible turning points have to be 4, because 5 minus 1, 4. What else? What else did it say? It's zeros, possible number of zeros. So it has to have at least a minimum number of zeros of 1, but it can have up to 5 zeros. Because remember, the notes aren't there, but we'll go over it. And then, yeah, so let's see. So degree is odd, leading coefficient is negative. Sorry, I didn't mention, I didn't do the end behaviors, apologies. So yeah, so if it's negative, then the end behaviors has to go from quadrant 2 to quadrant 4. So as x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, y goes to negative infinity. The function can have at most 5 intersects, or the function can have at most 4 turning points. And specifically, it can only have 0, 2, or 4 turning points. It cannot have a single turning point or 3 turning points, because remember, it's an odd, and it has to have an even number of turning points. So these are possible. And possible graphs of a 5th degree polynomial function with a negative leading coefficient. So these are all possible. You can have a graph that goes like this, graph that has 2 turning points, graph that has 1, 2, 3, 4 turning points, or a graph that has 1, 2, 3, 4 turning points, but the x-intercepts in this case are 1, 2, 3, 4, 5, and in this example, the x-intercept was just 1. Or another example is you have 1, 2, 3, 4 turning points, but 1, 2, 3, 4 x-intercepts. And we're going to get into like how to actually determine which one of these 5 possible. You're gonna learn techniques to get more specific. So right now we're just kind of doing a general overview. You're just learning some basic stuff, but later on you're gonna learn some cooler things. Okay. So example 2, we have an even degree polynomial. So that's a 4. So if you have 4, number of turning points can be 3, because n minus 1, 4 minus 1 is 3. We know that, excuse me, an even degree polynomial can only have an odd number of turning points. So since it can only have 3 turning points maximum, the only other possibility is 1. So you can either have 1 turning point or 3 turning points. It cannot have 0. It cannot have 2 or 4. So 1 or 3 is the only possibility. And what does it extend from? And behaviors. So since the leading coefficient is positive, it's going to have kind of like a regular y equals x squared shape. So it's going to be y positive infinity for both. And then here, 4 x-intercepts are possible, and maximum 3 turning points, 1 or 3. And these are the 4 different possible graphs for this specific example. And we're going to fill out the chart here. So here we have a degree of 1. And if you have a degree of 1 possible x-intercepts, remember, just 1. It's just equal to n. And possible number of turning points, n minus 1, so 0. For a degree of 2, 0, 1, or 2 possible x-intercepts, possible number of turning points, 1. If you have a degree of 3, possible x-intercept, remember, for odd degree, you have to have a minimum of 1 x-intercept. So you cannot have 0 here, so it has to be 1, 2, 3. And then possible number of turning points, 0 or 2. Remember, you can only have even numbers. Degree, 4. So 4, you can have 0, 1, 2, 3, 4. All the values from 0 to 4. And possible number of turning points, only 1 or 3, because you can only have odd values. Degree of 5, start from 1, 2, 3, 4, 5. For possible x-intercepts and possible number of turning points, remember, you can only have even numbers, so 0, 2, and 4. All right, I think we're going to do the last question now for this live session. Let's see what they're asking. Determine the key features of the graph of each polynomial function. The key features of the graph. use these features to match each function with this graph. State the number of x-intercepts, the number of local max min points, and the number